So this is for the Earth GeoTrack, and our next presenter is Emily Dorne. Emily Dorne is a lead data scientist at Driven Data, where she develops machine learning models for social impact. Her expertise lies in classifying animals in camera trap videos to support conservationists, identifying harmful algal blooms to support water quality managers, and helping data scientists consider the ethical implications of their work. She's passionate about using data for social good and has previously worked with the Bill and Melinda Gates Foundation, Stanford Center for International Development, and the Brookings Institution. So take it away, Emily.
Thank you so much. So hi everyone, my name is Emily Dorne, and I'm going to be telling you today about using satellite imagery to identify harmful algal blooms and protect public health. So I'm a lead data scientist at Driven Data, and Driven Data is a data science and machine learning consultancy in the social impact space. So I get to work across a lot of really interesting domains, things like financial inclusion for women, to wildlife conservation, to work in the anti-human trafficking space. And today I'm going to be talking about cyanobacteria detection. So even though we work across a lot of different domains, we do have consistency in the type of work that we do. So one of the main things that we do is we run online machine learning competitions. And these are a really great tool for exploring the predictive problem space, and basically allows us to answer, is this problem approachable from a machine learning perspective? What are some of the top methodologies for approaching this task, and how accurate are those approaches? We also do direct consulting work, so this is where we're working directly with clients, and the shape of that work really depends on the problem at hand and the context, and so the outputs of that kind of work can range from insights in a slide deck to a user-facing web application that's running trained machine learning models. And lastly, we devote some time to open source projects. So you might know of Driven Data if you've heard of cookie cutter data science. If you are a data scientist and you haven't heard of it, please go check it out. I think you'll find it helpful. So it is a reasonably standardized project template structure that really aims to support collaborative and reproducible data science work. And sometimes our projects span all three of these areas, from competitions to direct client work to open source projects, and that's the case of what we're going to talk about today. So let me give you a lay of the land. I'm going to start by telling you what cyanobacteria is and why it matters, so there should be no subject matter expertise required to follow along in this talk. I'm then going to tell you about CyFi, which is an open source package that uses machine learning and satellite imagery to estimate cyanobacteria levels. And finally, I'm going to give you 3 takeaways that are rooted in the development of CyFi that should be applicable to anybody who's developing models, machine learning models from satellite imagery. And I'm going to do my best to not get tongue-tied talking about CyFi as SciPi. So what is cyanobacteria? Cyanobacteria is a type of microscopic algae, also known as blue-green algae. It's the most common source of harmful algal blooms in freshwater environments. Harmful algal blooms are also known as HABs, and basically they occur when there's excessive algae growth that produces toxins that are harmful to human health, that are dangerous to other mammals like pets, and that damage aquatic ecosystems because they can block the sunlight that organisms need to thrive. HABs pose a significant risk to inland water bodies like lakes, rivers, and reservoirs because these are commonly used for recreational activities and drinking water. HABs are also becoming more common with climate change because they're more likely to develop in warmer weather. The current way that HABs are monitored is typically via manual water sampling, and this is pretty much what it sounds like. Local water quality managers go out in a boat or off a dock, collect some water, and send that off to the lab for toxin analysis. Water quality managers then make decisions around what public health guidance to issue, and this largely depends both on the severity of the bloom that was detected, as well as particulars of state policy. So some states choose to give more of the awareness campaigns, building knowledge of what HABs look like. So they'll put up signs kind of like this caution sign that says, hey, HABs may be present, kind of neither confirm nor deny, but just build awareness of what they look like and tell people to avoid them and why. Other states will do this more directly, where if there's a bloom detected in a water body, they'll put up a sign saying that there's a bloom detected, or they'll close a beach until the bloom has passed. So manual water sampling is accurate, but as you can imagine, it's far too time and resource intensive to be able to perform continuously and at scale. This is where the promise of machine learning comes in. So machine learning is particularly well suited to this task because indicators of cyanobacteria are visible in free, routinely collected satellite imagery. So as you can see on the right-hand side of the screen, you see that bright green that's indicative of that cyanobacteria bloom. Machine learning models can also generate estimates of cyanobacteria in seconds. So it becomes feasible to do things like provide daily estimates of cyanobacteria for water bodies all across the United States, which would be completely infeasible if you were to try to do this just from manual water sampling. But this isn't just potential, this is now reality. So I'm very pleased to introduce CyFi, which is short for Cyanobacteria Finder. And CyFi is a Python package that uses satellite imagery and machine learning to estimate cyanobacteria levels in small inland water bodies. The goal of CyFi is really to help water quality managers better allocate resources for the manual sampling that they're doing and to make more informed decisions around public health warnings for critical water bodies like lakes and reservoirs. CyFi uses high-resolution, quote-unquote high-resolution, there is higher resolution, but Sentinel-2 satellite imagery, which is 10 to 30 meters. And this level of resolution is needed in order to focus on these small water bodies with rapidly changing blooms. This is a key difference from existing tools that do cyanobacteria estimation without machine learning, but with satellite data, and those use Sentinel-3 imagery. Sentinel-3 imagery has a resolution of 300 to 500 meters, and this is sufficient for cyanobacteria detection in oceans and coastal areas, but it's far too coarse for small inland water bodies. As you can see on the screen, the top image is a water body at 10-meter resolution, and the bottom one is at 300-meter resolution. The reason why existing tools use Sentinel-3 imagery is because Sentinel-3 has a sensor that allows you to spectrophotometrically approximate chlorophyll, which is a good approximation of cyanobacteria. It's not perfect, but it is highly correlated. The main innovation in CyFi is using Sentinel-2 imagery with machine learning just from the visual bands and not from the sensor that's only present on Sentinel-3. So this is the CyFi pipeline at a glance, going from input to core data sources, our model, and our output. So CyFi generates estimates for cyanobacteria at specific points. This mimics the workflow of the manual sampling that water quality managers do. So each row in the CSV is a sampling point, where the sampling point is identified by a date, a latitude, and a longitude. The two key data sources that CyFi uses is Sentinel-2 imagery, as we were just talking about, as well as land cover classification. The land cover classification helps CyFi take into account attributes in the surrounding area that may contribute to the formation of blooms. So one example of this is fertilizer runoff from agricultural areas. From those data sources, we derive features that are then passed into a model, and CyFi uses a light GBM decision tree model. And I'm going to tell you more about why decision trees are a really great choice here a little later in the talk, so I'm going to leave that here for now. The output, again, for each sampling point, we generate an estimated cyanobacteria density in cells per milliliter, as well as a severity level. The severity level is just discretizing those cell counts into 3 buckets, low, moderate, and high, and this is based on guidance from the World Health Organization, as different severity levels generally are recommended to correspond with different public health interventions. That said, not all states choose to follow WHO guidelines. Some states draw different thresholds and take different actions, and so that's why we provide the raw density counts as well. So let's dig in a little further to how we actually choose what satellite image we're using for the sampling point, and then how we go from that image to features that are then going into our model. So we're starting with our sample point. So as I said, each observation is a combination of date, latitude, and longitude. From there, we draw a bounding box of 2,000 meters around that point, and we look for imagery within the last 30 days that intersects with that bounding box. From those candidate images, we then select the most recent least cloudy image. So for each candidate image, we calculate the percent of pixels in the bounding box that are clouds, and then we use the most recent least cloudy one. And if all images have more than 5% clouds, then we just don't make a prediction for that point because we don't have enough data to be able to do so. Now that we have our image, we then filter just to the water area in that image using the scene classification band in Sentinel-2. And from there, we are finally at a point where we can calculate our features. These are generally pretty straightforward summary statistics from the band values of those pixels. So these are things like the mean of the B1 band, or different ratios between the red and the green, or the blue and the red bands, etc. But all of that is happening under the hood. So we've tried to make CyFi really as easy to use as possible. So you can pip install it, and then you've got a single line of code to run at the command line to generate those cyanobacteria estimates. So here it'd just be CyFi, predict, and then point to the CSV containing your sample points. We also have a convenience function that lets you predict just for a single point. So this can be helpful if water quality managers have received a public report from a bloom. A number of states have hotlines where people can call or submit photos in. And then they just need to verify that individual one. You can run it this way. It also makes it easy for all of you to just go try it out. You can run it on the water nearby and see if there's any cyanobacteria going on. So CyFi was trained and evaluated using ground measurements of cyanobacteria from across the United States. We had about 9,000 observations in the training set and 4,000 observations in the test set. And it can be hard to come up with generalizable accuracy numbers because exactly how well CyFi does in part depend on what samples are in the test set, because not all samples are easy or hard, right? This can depend on how big the water body is. Certain states can just be trickier to estimate effectively than others, how narrow the water is, the waterway is, the severity of the bloom, etc. So basically what we tried to do to get a better sense of accuracy was to do a direct comparison with the leading Sentinel-3 based tool. So the Sentinel-3 based tool is produced by the Cyanobacteria Assessment Network, which is known in short as CYAN. It's a collaboration between NASA, NOAA, and EPA. And so basically what we did is we took the 4,000 points in our test set and we said, okay, which of those points are in a water body that is large enough to be picked up by the resolution of Sentinel-3 imagery? And then for those points, we're going to see how well did CyFi do and how well did CYAN do. And what we find is that CyFi performs basically at least as well as the Sentinel-3 based tool. So in this plot, I'm showing you bloom detection accuracy. So this is a combination of true positives, correctly identifying when there's a bloom, and true negatives, correctly identifying when there's not a bloom. And the goal here of CyFi was really not to say we need to get better, like significantly better than Sentinel-3 accuracy. We're trying to say, can we even meet Sentinel-3 based accuracy with Sentinel-2 data where we're using machine learning on just the visual bands? So this is actually a really big success story because this allows us to then use the Sentinel-2 data, which has 10x the coverage of lakes across the United States compared to Sentinel-3. So this map on the right is showing you all the water bodies that are picked up with Sentinel-2 data. That said, CyFi is not perfect. It tends to be most accurate at low and high severity levels, which nicely aligns with the primary use cases. So this basically boils down to where not to look and where to look. So the low severity cases, knowing where not to look is very important because this allows us to better allocate ground sampling resources by deprioritizing water bodies where blooms are likely to be absent. In the high severity cases, this allows us to support public health interventions by quickly flagging the water bodies where severe blooms are likely to be present, and then water quality managers can choose whether they want to go out and sample to get a more precise reading of the toxin levels, or maybe they choose to issue guidance based on the satellite image and the CyFi prediction alone. In general, we don't think that CyFi is at an accuracy yet where it should be used for automatic issuing of alerts. The intended use is really to augment human-in-the-loop workflows and allow humans to make more timely and targeted decisions. So now that we understand what CyFi is and why it's useful, I wanted to share some learnings that we had from developing CyFi. So CyFi had kind of a unique development process that really spans the different types of work that we do at Driven Data. CyFi has its origins in a machine learning competition that we ran in collaboration with NASA to basically do a first pass estimate at the feasibility of this task. Can we even estimate cyanobacteria just using Sentinel-2 imagery with the visual bands? The answer is yes. So then we proceeded to the next stage of user interviews where we talked to water quality managers in a number of different states to really understand their real-world user needs and to basically ask the question, if you could have regularly generated estimates of cyanobacteria, how would this change your decision-making workflows? From there, we got into a model iteration stage where we were combining some of the different approaches that won the competition to really create a generalizable and accurate model. And then we brought this all together in a Python package, because as you can imagine, the code that comes out of a competition looks a lot closer to research code than it does to production code. And so we wanted to basically bring the final pipeline and model into a deployable code package that was capable of generating predictions on new input data. So the first takeaway that I have for you all is just because there's an image involved doesn't mean you need a neural network. So we ran this competition called Tick Tick Bloom, and all of the winning approaches used decision trees. And what we've seen in a number of other competitions as well is that decision trees are a leading approach for satellite imagery-based tasks where the output is point estimation rather than segmentation. So for example, we ran a competition in a very different domain. We were estimating snow water equivalent, which is also known as SWE. And SWE is basically how much water is there in snowpack. If you melt the snow, how much water do you get? It's a combination of both how deep the snow is and how dense the snow is. So similar sort of setup, you're using satellite imagery, and then you're estimating SWE at various grid cells across the western US, and that competition, decision trees also did very well. In an air quality competition, where again we were using satellite imagery to estimate PM2.5 at points around the globe, decision trees also won. So if you are also working with also working with satellite imagery, definitely consider decision trees for your task. Some of the key benefits is that they are quick to train, so this can make it really nice for iteration and experimentation. Inference is also quick, which is nice if you need to predict on a relatively frequent cadence. They typically don't require a GPU, which again is a good story for deployment. And then they also tend to be more interpretable than neural networks because they give you things like feature importances that provides additional insight into the decision-making rationale. The second takeaway I have for you is use an out-of-sample dataset to see if you're getting the right answer for the wrong reasons. So I'll tell you a little story here. We were in the model iteration phase, and we ran CyFi on some newly collected data that we got from summer of 2023 in California, and CyFi did not do well. And we were like, what is going on here? And it turned out that the model was estimating high levels of cyanobacteria in most cases. And we were looking at the images, and we were seeing these high severity estimates, even in cases where the water body looked very dark, didn't have any of those kind of canonical signs of that bright green bloom. And the culprit was land pixels. So see, at this time, our pipeline looked like this. We drew a bounding box of 200 meters around the point. We got images within 7 days of the sample point. We didn't worry about clouds because we had a small bounding box, and we calculated features from all the pixels in the image, and then we averaged predictions if we had multiple images within the week because they were all recent. So this is a case of getting the right answer for the wrong reason. So what had been happening in our test set is that the model had been correctly estimating high levels of severity, but not because of what it saw in the water. Rather, in our test set, points near land tended to have high values of cyanobacteria, so our model had incorrectly learned, land, high severity. But in the out-of-sample set, this was no longer the case, and we had points near land that could be low, moderate, or high severity, as is the case in the real world. So the fix here is filter to water pixels. And this actually had a cascading impact on our pipeline. So we say, okay, we're not going to calculate features from all the pixels in the image, we're going to filter just to the water pixels. But if we do that, then we really need to draw a larger bounding box to make sure that we're getting enough pixels to be able to make a good estimate. So we draw a larger bounding box that's now 2,000 meters instead of 200 meters. But if we're going to have a larger bounding box, then now we really need to worry about clouds, because we've got an increased chance that we're going to have clouds in our bounding box, and so we introduce this cloud screen where we basically toss out images that have a bounding box with more than 5% cloud pixels. But if we're going to get picky about clouds, then we need to look further back and look for images within the last 30 days to be able to increase the chances that we have an image that we can use to generate the estimate. And typically within 30 days, it still has enough signal to provide a useful cyanobacteria estimate. But if we're going to look further back and go all the way back to 30 days, then we can't be averaging predictions across multiple images. We really just need to use the single most recent image. Otherwise, we're just going to average out any short-lived blooms. So the particulars of exactly what changed in the pipeline is less important, and this is much more a story of how useful the out-of-sample data set was in showing us where our model was making the right prediction for the wrong reason, and all of these changes ultimately led to a much more generalizable model. And the last takeaway I have for you is that visual examples are really useful for helping users build confidence and trust in machine learning models. So machine learning models can feel like a black box to the people who aren't developing them. And this was something that came up in our user interviews. So even with states who had a use case that was really a great fit for CyFi, and it was clear to us how CyFi could really plug in and help save time, there was still this reluctance, right, of why should I trust this machine learning model, right? It gives me a number, and why should I trust that? And I think it can be tempting as a data scientist to be like, I will give you metrics. I have precision, I have recall, I got bar plots. But really, it's the visual examples that I think are one of the best ways to help users build trust in a model and develop intuition for where the model is more or less reliable. So we ended up building in visualization functionality into CyFi. It's called the CyFi Explorer. There's an image of it on the right. And basically what this lets you do is after you have generated your predictions, you can then launch the CyFi Explorer, click on those sampling points, and look at the satellite imagery that was used to generate that prediction. This took maybe a day to build as an MVP. It's a Gradio app. It's really quick to build. And so this is one of those examples of like the low effort, high reward. It's probably one of the most impactful parts of CyFi because it allows people to realize, hey, a machine learning model can actually do this task. So to give you this experience of it as well, you can imagine being a water quality manager and talking to me about CyFi. If I show you a bar plot with precision and recall numbers, this is not going to give you any indication into where the model is doing well and doing poorly. This is not to say that these metrics don't matter. They're very important to us and our processes and understanding what model is most effective and informs our experimentation, but it's not the way that we are going to build trust. Contrast that with giving actual examples where you can toggle through. This works because you can basically see the ground truth. Like the ground truth is visible. So even if you can't see the difference between 40,000 and 45,000, you can see the difference between low severity and high severity. So giving people a way to actually peruse the predictions helps them build the intuition for the types of decisions that the model is making. And this can really help support adoption of machine learning models into human-in-the-loop workflows. So to put that all on a single slide for you, the 3 takeaways that we learned in the process of developing CyFi: just because there's an image involved doesn't mean you need a neural network. Use an out-of-sample data set to see if you're getting the right answer for the wrong reasons. And visual examples help users build confidence and trust in machine learning models. So if you're interested in learning more or trying it out, you can find out more information at cyfi.drivendata.org. And of course, it is an open source package, and we welcome contributions. So if you're interested, you can go to our GitHub, which is drivendata.org. The package, again, is called CyFi, and I look forward to reviewing your PRs. So thank you so much for your time and attention. Again, my name is Emily Dorne, and you can learn more about CyFi at cyfi.drivendata.org. Thanks so much.
Thank you, Emily. Okay, so we're taking questions. As a reminder, you can ask in person, but also on our Earth, Ocean, Geo, and Atmospheric Sciences channel. You can comment questions there. We actually have one already, so I'm going to read that off. Bobby Jackson said, have any state environmental agencies used this in operations?
Not yet in operation, so we are basically currently talking to states and finding people to run pilots with because more manual data is being collected, and that allows us to do additional validation. And then we're also talking to NOAA to basically see if this could get supported at a federal level because that would be a lot more efficient than having each individual state have to kind of set up their own deployment.
It makes sense, I think, just getting it funded and getting a wider training set.
Exactly, that's one of like the main levers. I think one of the, in terms of like a larger data set, it's not just a larger data set, but it's also more true negative cases. So a number of states will only conduct the toxin analysis if they suspect a bloom. So we tend to have, an over prevalence of cyanobacteria in the data set that we have. And so having those true negative cases that have been confirmed by a toxin analysis would be really helpful. Exactly, or that, yeah. That's even harder to get funded, but yes.
Any questions in the audience?
I was curious if you could describe the image searching and fetching process, like where the data are hosted and how it's downloaded and things like that.
Yeah, so we use Microsoft's Planetary Computer to access the Sentinel-2 imagery. It allows us to run the queries for the intersection of the bounding box and then download it as well. I think we do a little bit of transformation with rasterio, but then ultimately we're just converting it to NumPy arrays, and we're only saving out that bounding box, and so that's actually really small. That gets saved to a cache on the user's computer that's routinely cleared, but if you were to run the same query twice, we wouldn't then re-download that satellite imagery.
Great presentation. I was curious about the in situ data. What exactly was it that you guys used? You had a lot of points, which is awesome.
Yeah, the in situ data. Yeah, so this was basically, let me see if I can go back and find that map. Here we are. So this was actually in preparation for the competition that we ran. So NASA basically worked with data providing organizations all over the US. So we had, I think we ended up using data from 13 data providers because they provided cell density. But initially, we got data from even more than that. And so there was a whole process that NASA helped with in terms of like aggregation and collection of that data. And then we did additional like standardization to then use it for the competition and then continue using it for the development that happened afterwards. And that data set is actually now public, so it's on the CBAS archive with documentation so that other people can use and take advantage of it, because this was actually a really novel part of the competition, was just getting a data set of this size of the ground sampling measurements.
It might it might be too far to go back, but would you mind summarizing again how CyFi compared to the Cyan, I think it was? I think I didn't quite, oh, it's right there. I don't quite understand your bar chart there.
Yeah, so this is looking at basically total accuracy. So basically of all the points, what percent are we getting correct? So that's 72% for CyFi and 66% of Cyan. And then the shading is just indicating what portion of those correct cases are true positives and true negatives. So you'll see that like one of the differences between CyFi and Cyan is the ability to detect true positives. That teal bar is a lot greater on the CyFi side than the Cyan side.
So ideally, would they match if it's exactly the same? I mean,
No.
like, would ideally they match if they're getting the same performance, or what is the ideal situation, I guess?
Yeah, so basically what we have is we have the CyFi prediction, we have the Cyan prediction, and then we have the ground measurement, ground truth. So basically the ideal case is that this bar chart's 100% that says we got everything right. So this is basically saying how much did we get right? We get more right than Cyan does. But the general takeaway that I was making was more that like we're basically trying to say, can we do at least as well as the Sentinel-3 based tools because we get 10x the coverage? We actually do a little bit better than the Sentinel-3 tools as well, which is like an added bonus.
Hi, thank you for your talk. I had a quick question, two quick questions. One was the land cover data set. You used a CCI land cover. What is the resolution of that, and why not use the ESA version of the land cover? And the second question is, it seems to me that it's almost like a sampling approach where you know exactly where to sample, so you're going to get to draw the 2,000 meter box. But if you oversample a specific region and the lake is actually very, very large, the threat level assessment for that point is not an indicator of the threat level for the whole water body, right? So I was curious on your thoughts on that.
Yes, the land cover classification, if I'm recalling correctly, this is at, I think, 300 meter resolution. So this is quite coarse, and so we're basically just looking up that single pixel where the sample point, what is that land cover classification for that area. So if we're in a really large water body, then our land cover classification is just going to be water. But if we're in like a much smaller water body, then we're going to end up picking up on whether the surrounding area is cropland, shrubland, agricultural, et cetera. And then to the point about the sampling, so I'm not sure I totally understood the question, but let me try to take a stab at it. So basically, we're not choosing when to sample. Basically, what has happened is that we have ground truth measurements from water quality managers. They choose designated sampling points, and they sample those based on resourcing and a set of other things. And so Sometimes that's informed by, suspected blooms. Sometimes states have like more routine sampling where they go out every month. So we're not really at risk of like us choosing, what to sample and then biasing it that way. But I think the other part of your point was around what happens if you're in a large lake and you've only sampled one point of it. So you're not limited to only putting in one point for a lake, right? You can put in multiple points around a lake. One of the features that I would love to see developed here is actually to accept a polygon as input and then grid it up into the 10-meter grid cells and then pass those into CyFi. It would just be a small pre-processing thing that would then allow us to have a view of like the more continuous lake coverage.
Okay. I think we're out of time, but we'll be back here at 3:50 for a talk on XCDAT. So hope to see y'all then. Thank you,
Thanks.
Emily.